Now that we have performed a Y plus study and a mesh study in 2.5D, we can perform the 3D simulations. As previously mentioned, the 3D simulations can take hours to mesh and solve, so try and collect as much information as possible from 2.5D before jumping in. Like the 2.5D simulations, let's set the geometry up, create an auto-generated mesh, and set up Fluent. This will allow any issues that may arise, like missing faces or incorrect directional vectors, to be quickly fixed. Now let's duplicate this simulation and check the geometry out. So you can see the geometry that's been created. Let's go back, suppress these subjects. You can see the fairing and the wheels that were initially created. The inner domain that's simply been extruded out an extra width to 650 mil. And the outer domain that's been extruded out by 5 meters. Now we want to make sure that the inner domain has been extruded out such that the mesh has room to expand from the surface, and the outer domain extruded out 5 meters such that there isn't any pressure gradients from the fairing to the far wall. We then go through the procedure of booleaning out the inside and outside domains, making sure to include the wheels within the boolean functions, and then we can make these extrude cuts, and also this surface, which is the body of influence. The symmetry function cuts the body in half, and then we can delete out the fairing that's remaining. This extrude takes a cut out of the XY plane. Now when we go into here and we suppress this body, we've used a blended function that blends the edge of the wheel. So what would happen is that if the blended function wasn't there, we'd create a very skewed element in this corner, leading to issues with the mesh. So this improves the mesh quality. So it's performed to all 4 edges where the wheel connects to the ground. Now exit that and let's go into the mesh. With the mesh open, we'll have to make some few changes. First, delete any connections that may be created due to the body of influence and the outer domains. Then go through and fix up the name selections. Because we have extra faces, not all the name selections will be correct. So make sure we've got an inlet, a sky that goes from the top to the side surface of the outer domain, the ground, which also encompasses the fillet that we created, an outlet, symmetry 2 with that surface there as well, keep that in mind, the fairing, and also make 2 new selections for the front and rear wheel. Keep in mind, if you do select the fillet, that may also be a ground. Fluent will throw up some issues saying that you've created a named selection for one surface twice. And then go through and delete the meshing procedure that was previously created, and we'll remake them. Before we mesh and check the worksheet out, delete the sweep method around the actual fairing, add a sweep method to the outer domain, making sure that we've got an automatic source and target with all quads, and just leave the swept number of divisions to default. Include the body of influence and just leave it as default. So if you're at a current number, if you hit 0 and press enter, it'll just take it back to its default value. Then go through and implement the meshing worksheet as previously. So keeping in mind to start off at the fairing and then start to mesh the adjacent surfaces. So you can see what's happened there, and that was the next mesh, one afterwards. There you go. Then just generate the mesh. Again, it doesn't really matter what the mesh actually looks like as long as something actually generates. We'll go through and refine it later on. We just want to make sure that we've selected all the surfaces with the appropriate named selections and that the boundary conditions have the appropriate velocity vectors. So run through the Fluent setup. The model is a K-Omega SST, curvature correction and product limiter. And then go through and check the boundary conditions. So we have a fairing that's a stationary no-slip wall. For now, leave the front wheel as a stationary no-slip wall as well. Ensure that the ground has the appropriate wall velocity of 40 meters per second in the negative Z direction. Make sure that the inlet is at 40 meters per second. The outlet is at 0 gauge pressure with an average pressure specification. The rear wheel is the same. And as the sky, you can just implement a moving wall with a specific shear of 0, and then the symmetry should be automatically identified. Throw in the appropriate reference values, got a coupled scheme, and then change the current number to 100, add any monitor points, and then initialize and run the actual simulation. You can see here that the monitor points, it's again not really worried about if they're converged or not. We just need to make sure everything's going the right direction, and then go back to your contours, and you can quickly plot the velocity on the symmetry plane. You can plot your velocity vectors. And just make sure they're all going the correct direction. So now that Fluent has been set up, let's go through and add the rotating wheels to the components. So first what we're going to do is go into our meshing module, go under coordinate system, and create a coordinate system using right-click coordinate system. Create a coordinate system for the front and rear wheel. So you can see here the geometry that's been selected is the wheel, and that gets us an origin for the XYZ for the front and the back, and just note those numbers and make sure they're down somewhere. So what will be different is that if we go into our boundary conditions, we go to the front wheel, we can see that we've got a moving wall at 160 rads per second, so it's your speed divided by your radius. Those values from previously, put them into the origin, and the axis of rotation, which is X, so you can use the right hand rule to determine if it's in the correct direction. And for the rear wheel, let's do the exact same things. So 160 rotational, different origin and the same rotational component. Run through the simulation and just let it go for 50 or so iterations. It's again, don't really care what's happening with it. Let's bring both these simulations into one results file. And we can see straight away that when we apply the vectors to the front wheel with local and 0.1, we can see that the basic setup with the rotating wheels actually has wheels rotating in the direction that we want. And the basic setup has nothing.